What would you do if you could perhaps freeze time? If you could snap your fingers and everything around you stopped? This idea is not new, and it is even the basis of one of the best films ever made in the history of world cinema. But how much science is there behind the idea of freezing time? I don't know. And no one does. A large part of our scientific understanding boils down to understanding how matter changes over time. Physics is the study of the change of position over time. Chemistry is the study of changes in chemical composition over time. But even with time assuming a central role in science, we know almost nothing about what time really is. We know how to measure time with clocks, but beyond that, time is considered a simple and immutable fact. And it's quite rare for a theory to explore the origin of time. But even knowing little, it's clear that the idea of freezing time throughout the entire universe is absurd. And the reason is that if time were completely frozen, nothing would happen in the universe. Everything would be static and nothing would change, or at least that's what it seems. Stopping time is the worst thing that could happen. But to understand why, there is a question we need to answer first. What exactly does it mean to freeze time?
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
When the best movie in the world used the idea of freezing time, it had a narrative motivation to create the effect, without worrying about the laws of physics or Adam Sandler's career. But the narrative function of this video is to teach physics. So we are going to freeze time using physics. Theories of physics are constructed as a set of fundamental laws represented by mathematical equations. It is possible to divide the laws of physics into two major categories: dynamic laws and static laws. Dynamic laws are those that directly depend on time, like Newton's second law. Force is equal to mass times acceleration, and acceleration is the change in velocity over time, and velocity depends on the time during which the force acted. Static laws, on the other hand, are physical laws that hold true in the same way, regardless of how much time passes. For example, if you kick a ball in space, it will continue with the same mass and the same velocity. And the multiplication of these two quantities is what we call momentum. And this value is the same now, a minute from now or a year from now. And if, instead of one, you have 1,000,000 balls being kicked in different directions, the sum of their momenta will remain the same. This fact represents a static law. The total momentum is conserved. This is true all the time. A force from Newton's second law can constantly change over time, but the total momentum is always the same now or a month from now. Conservation laws do not vary with time, whether it's the conservation of momentum or energy. With dynamic and static laws in mind, it is possible to give a more precise meaning to what it would be to physically freeze time. Freezing time means suspending dynamic laws, but without violating static laws. Newton's second law doesn't occur, but the total momentum is still conserved. And this helps us answer what happens physically if we freeze time. And just to be clear, from now on this video will become quite hypothetical. I will say the magic words and make time freeze here on my side. Editor, please freeze time. Thank you, editor. If possible, leave a thumbs up on the video for the editing team. They deserve it. You might have seen a flash of light when I magically froze time. This wasn't just to make the special effect more practical. When I froze time, all the particles in the region stopped moving, but this microscopic movement carries energy, and this energy can't just disappear. Don't forget that dynamic laws, like Newton's laws, stop working when time freezes, but static laws do not. Conservation of energy is a static law and not a dynamic law. So, the energy that was stored in the movement of the particles was emitted as light, and it was the light from this energy being removed that you saw. But wait a minute. If I froze time in this region of space, how did the light move to escape it? Here comes a curious fact. There is a law of physics that deals directly with motion, but it is not a dynamic law. The speed of light is absolute. Light always moves at the speed of light, regardless of the situation or the observer. It's as if light doesn't care about time. If freezing time is equivalent to maintaining only the static laws of physics, light could pass through a region of frozen time, as could anything traveling at the speed of light, such as electric and gravitational fields. Although light can escape our frozen time, it won't be able to interact with what's inside this bubble. Reflection of light is a dynamic process for matter. As the dynamic laws stop working, light would simply pass through whatever is inside the frozen time bubble, as if it weren't there. In other words, the frozen time region would be invisible, which would be dangerous, because it would be very easy to stumble upon it accidentally. This raises another question. What will happen if I enter the frozen time region? Our intuition tells us that some law of physics will be violated. But the question is how to minimize the number of violated physics laws. When an object is moving, it has momentum and energy. Upon colliding with a frozen time region, this momentum and energy must be preserved, regardless of what happens. Because conservation laws are static laws, which hold true regardless of time. And one way to keep conservation valid would be for the edges of the frozen time region to act as a kind of portal. For example, when I tried to cross the frozen time region, I would be transported to the other side, as if I had passed through a portal. In this way, all the energy and momentum I have is perfectly conserved. And this only violates one law of physics, because I kind of traveled faster than the speed of light for a short period of time. But if Adam Sandler can, so can I. And here's something curious. If the region with frozen time acts like a portal, and if it is transparent, it's almost as if the region isn't there. It is invisible and is traversed by anything that comes close. For practical purposes, it's as if the region has been deleted and no longer exists, which shows how crucial the passage of time is to our understanding of the world. In this attempt to freeze time, we inadvertently came to the conclusion that without time, things basically don't exist. Removing the passage of time seems equivalent to completely deleting a region from the universe. I did say that freezing time would be the worst thing someone could do. Existence seems connected to time, so perhaps it's no coincidence that the true origin of time is as mysterious as the very origin of the universe. Thinking this way, freezing the time of the entire universe would be like erasing the universe from existence. Freezing all time would be the end of everything, which is a perfectly reasonable conclusion. But if that were the only reasonable conclusion, I wouldn't need a dramatic transition at this point in the video. Perhaps time is already frozen. Maybe our perception of a linear time that flows from the past to the future and the idea of cause and effect is the wrong way to look at time, and perhaps even the universe itself. And yes, I know this is a bold statement, but it is not a statement without basis in physics. One of the greatest quests of modern physics is to unify our theory of gravity with the laws of the quantum world, which would be a theory of quantum gravity. And interestingly, many proposals for quantum gravity completely erase time from the universe. Seriously, this problem even has a name. The problem of time. The problem of time arises due to the difference in how two of our best physical theories deal with time, relativity, and quantum physics. Although quantum physics is full of non-intuitive phenomena, the quantum world works exactly like what we are accustomed to. Time passes, and with that, things happen in space. It's as if space were a canvas, a blank slate, and time were the brushstrokes that create an image. General relativity, on the other hand, sees time and space in completely different ways. The presence of massive bodies, like stars and planets, distorts both time and space. Two different observers, in two different places, perceive measurements of time and space differently. Space-time itself is affected by what happens, and the notion of time is relative, not absolute. In a more mathematical way, in quantum physics, the equations describe what happens in time. In general relativity, the equations describe what happens with time. So, which of these two views of time is the better one to describe quantum gravity? Perhaps neither. And I need to explain a bit more about how to create a quantum theory before explaining the problem of time. One way to create a quantum theory is to take some equation from classical physics and perform a process called quantization. In this process, you add quantum properties to the terms of the equation, properties such as probability, uncertainty, and complementarity. The problem is that not every equation is easily quantized. For example, Newton's second law cannot be easily transformed into a quantum equation. The closest thing to a second law of Newton for quantum physics would be the Schrödinger equation, but even visually, they are quite different. Fortunately, there are other equations capable of describing motion, alternatives much more elegant than Newton's laws from the perspective of quantization. For example, Hamilton's equations written with Poisson brackets become the Heisenberg equation when quantized, and you don't need to understand anything I said to see that these two equations are quite similar. This is the art of quantization, finding the easiest way to transform classical equations into quantum equations. The problem of time arises when we try to quantize gravity as described by general relativity. Let's imagine a simple scenario, a single planet orbiting a single star. Knowing the mass of the two bodies and their relative velocity, it is possible to use the equations of general relativity to describe how the planet moves around the star and how this movement affects the structure of time and space. At each moment, it's not just the planet that changes position. The very space around the planet is curved by the movement. Even the rate at which time passes is affected by the movement of the two bodies. Even in a simple problem like this, general relativity takes into account the very structure of space-time. And that's what makes the equation so complicated and so difficult to quantize. And this is where a daring and bold trick comes in. Indeed, it's easier to quantize gravity if we freeze time. And how exactly can we do that? When we solve the equations of motion, we know how the planet will move around the star for all of the future. And we also know where the planet was in the past. The equations determine the behavior of bodies throughout the history of space and time. In other words, dynamic equations are equivalent to the entire historical line of motion. It is possible to rewrite physics in terms of these complete historical lines, that is, to replace the equations that describe motion moment by moment with the complete and static solution for all moments in time and all points in space. And this generates a completely static formulation of physics. In this formulation, all time has already happened. Past and future are no longer different. All points in time are equally accessible, just as all points in space are. Calculating what happens 15 months in the future or in the past is equivalent to calculating what happens 15 kilometers to one side or the other. Mathematically speaking, the dynamic view and the static view yield the same results, but the philosophical conclusions they suggest are quite different. We exchange a dynamic view, in which the universe changes little by little and where causes generate effects, for an eternalist view. In eternalism, the future is as determined as the past. Time exists as something broad and complete, not as a process that advances second by second. It's as if the entire universe were a block of frozen stories, with one of the block's directions representing time. This is the block universe view, in which time is already frozen. But it gets worse, because quantizing this block universe is still not that easy. However, it can be made easier by making another change in perspective. In Einstein's relativity, time and space coordinates are not the only ways to describe spacetime. It is possible to switch from a description that uses position and time to one using a mixture of the two. For example, light cone coordinates use paths of light rays to describe changes in the structure of spacetime instead of measurements of distance and time. And in light cone coordinates, time and space are mixed. In this case, one of the light coordinates is the position plus the speed of light times time divided by the square root of 2. This coordinate is neither space nor time. It is a coordinate that mixes space and time, which doesn't mean much to our human intuition. But the moral of the story is that it is much easier to quantize gravity by choosing strange coordinates like these. So, the quantized version of general relativity doesn't even have a direct representation of time. Quantum gravity describes the universe in completely arbitrary coordinates, with no direct relation to our everyday experience of the universe. Quantum gravity not only freezes time but also shatters the very idea of time among these more convenient coordinates. The best description of the universe is in terms of mathematical concepts that don't even have recognizable names but are easy to quantize. The problem of time is the conflict between the idea of a block universe seeming like a good description of the universe but also destroying the intuitive concept of time. On one hand, describing the universe well is the goal of any physical theory, but on the other hand, time does seem to be part of this universe. So, how much sense does it make to abandon time? Is it possible to save time even in these block universe theories? Maybe. In a block universe theory, the variables are still indirectly related to time and space as we know them. And it might be possible to find a way to unscramble the coordinates and recover a more intuitive idea of spacetime. Recover the notion of time not as something fundamental to the universe, but as a combination of other variables. It would be like slicing the block of the universe into small sheets and trying to reorder them using our intuitive concept of cause, effect, and time. The problem is that there is more than one way to order the universe that makes sense, and no one has found a satisfactory way to define time using this process. Another alternative is to just push the boundaries and impose that time exists as an additional law for this theory. It works, but it's unpleasant. It seems like a violation of that idea of simplicity from Occam's razor. And the third alternative is to abandon time. The universe is not a block of frozen time. It is just a block of events and occurrences without a well-defined order. What we perceive as a story, an order of cause and effect, is just one of the infinite possible ways to slice and order the block of the universe. The universe is a block, and each direction within this block represents a different way of viewing the universe. And within this infinity of perspectives, there is a specific direction that is what we call time, with each moment of the universe being just one of many possible perspectives. Time is a random direction in the block of the universe, which we only perceive because we are moving through that direction. In this case, the idea of time is just one of the possible ways to view the universe, and it might not even be the best one. Freezing time might be a terrible idea in our intuition, but it might be the best idea in science. But then I would like to know what you probably already thought at some point in this video. If you could freeze time, what would you do? Type it for me here in the comments. And see you next time. Thank you very much.